look at defining and graphing exponential functions. And if you haven't seen exponential functions before, this is completely different than other areas of algebra, such as linear and quadratic functions. And we define an exponential function like this, as f of x equals a to the x power. Now, look at this. The variable, the x, is my variable, and it is an exponent. Usually we have x to a power, like x squared, x cubed. This time we have something raised to a power of x. Now this a, the something we're talking about here, is called my base, and it has some restrictions. First, a is a real number. Alright, now we also have a is positive. We don't want negative values of a. And we pick a to be positive because if we had, for example, the square root of a negative number where x is 1/2 of a negative base, that's not defined. Okay, so we want something that has a good domain. And also, we don't want a to be 1 because otherwise it's kind of boring, so we don't really think about it. Alright, now let's try to get a handle of what these things look like through an example. So I'm actually do 2 examples here, and I'm going to set them up with charts. Okay, so I have 2 examples. I have f of x equals 1/2 to the x power, and I have g of x equals 2 to the x power. And I'm using a chart here. I'm going to fill in different values for x to see what kind of values we get. Okay, now actually I think what I'm going to do is I'm not going to do these in the order they're written. What I'm thinking first of all is let's let x be 1. Okay, because when x is 1, I can easily think of a power. So for example, f of 1 means 1/2 to the first power, and 1/2 to the first power is just 1/2. On g of x, 2 to the first power is just 2. Okay, now if I let x to be 2, and f of x, f of 2, I have 1/2 squared. That's 1/2 times 1/2. I get 1/4. And for g of x, g of 2 is 2 to the 2 power. That's 4. Alright, so something like that. Okay, you may remember that anything to the 0 power is 1. For both of these, I have 1 when I plug in x to be 0. Alright, now let's do the negatives. So if you remember, a negative power just means a reciprocal. We had a rule that said something like this. A to the negative n power is 1 over a to the n. Okay, so for example here, if I let x to be negative 1, 1/2 to the negative 1 power means you take the reciprocal and raise it to the first power. So that's going to be 2 to the first power. And if I do that into g of x, that means I have 2 to the negative 1 power, which would be the reciprocal, so I get 1/2. Okay, now if I do negative 2, that's 1/2 to the negative 2 power into f of x, which means I take the reciprocal of 1/2 squared, so that's 1/4. Reciprocal of that, we get 4. And in g of x, 2 to the negative 2 power means the reciprocal of 2 squared, so I get 1/4. Okay, and so you can kind of notice here, there's a relationship definitely between these two functions, right? And when you plug in opposite values, they kind of go to opposite places. Okay, so these definitely have some sort of relationship. But we're not really interested in that right here, okay? What we're interested in is looking at the graphs of such things. Okay, so how do these things graph? And we're going to graph both of those right now. Okay, so I'm going to graph f of x and g of x. And one thing I want to point out is, and you can kind of see this from our table, how would these exponential functions ever be negative? I mean, I take a positive base, raise it to an exponent, that's never going to be a negative value. So these graphs are never negative, they never below the x-axis. Also, how could I get 0? 2 to what power equals 0? Well, I can't really think of anything. I don't think you could either, really, because you can't get 0, alright? So these things are never negative and they're never 0. Okay, so if I graph f of x, and we can start with 0 if you want. So if I plug in 0, I get 1. And if I plug in 1, I get 1/2. And at 2, I get 1/4. And at 3, I get 1/8, something like this. And in the opposite direction, negative 1, I'm at 2. And at negative 2, I'm at 4, something like this. And so you can see you're going to have a curve that kind of goes something like this. Alright, now let's do the same thing with g of x, and then we're going to talk about a few characteristics of these graphs. Alright, so now graphing g of x, we can look at that real quick. Let's see, if I plug in 0, I'm at 1. Going in the negative direction, I go 1/2 at negative 1, I go to 1/4 at negative 2. In the positive direction, at 1, I'm at 2. At 2, I'm at 4, so this thing is growing very fast, and it's going to grow off the chart. Even at 3, I'm at 8. And the graph's going to look something kind of like this. And so if you notice, these graphs look opposite of each other. And in fact, that is the case. So over here, if I have an a that's between 0 and 1, like I had here, notice what's going to happen. My end behavior, as I'm going out to infinity, I approach 0. And as I'm going to negative infinity, f of x is going to approach positive infinity. So the right behavior is 0, the left behavior is infinity. And so I have a horizontal asymptote and y equals 0. All right, now on the g of x side, it's going to be the opposite. Okay, so for a greater than 1, my left behavior is going to go to 0, and my right behavior is going to go to infinity. So as x gets larger, this thing's going to blow up very, very fast. Okay, now let's use this fact to graph some exponential functions, and hopefully this makes sense. Okay, so for a here, we have f of x equals 1/3 to the x power. Now this is an a is less than 1 case, so I kind of know what it's going to do. I know that it's going to cross at 0 at 1, okay, and then as x gets larger, this thing's going to go to 0, and as x goes to negative infinity, f of x is going to blow up to positive infinity. So your graph's going to look something like this. Even without graphing any points, I kind of have an idea. It's going to go like that. If you wanted to plot a few points here at 1, I'm at 1/3, so this is the point 1, 1, 3. At negative 1, I'm at negative 1, positive 3, right, because it's reciprocal exponents. If you wanted to graph at 2, you're at 2, 1/9, and so on. All right, now for b, I have negative 4 to the x power plus 1. Now, you may think, wait a minute, I thought I was supposed to have positive bases. Well, that's true. The negative here is not associated with the x power here. This is not saying negative 4 to the x power. That would be bad. Okay, this is saying negative 4 to the x. In the order of operations, exponents are more powerful than multiplication, so the negative is tacked on after the exponent. Okay, so what does this do to the graph? All right, so I'm going to plot 4 to the x first, and then we're going to have to make some adjustments. So at 0, it hits 1. It always hits 1. And then my graph's going to do something like this. It's going to blow up really quickly. Okay, now this would be if we had just 4 to the x. Okay, what does the plus 1 do? The plus 1 shifts everything up. So now my graph would look something like this. Okay, and that would be 4x plus 1. But this is negative 4x plus 1. So what happens there? The negative flips everything down. The negative 4x would hit at negative 1 and go something like that. The plus 1, and this is what we're actually trying to graph, would raise everything up 1 unit. So it's going to go something like this, okay? And this asymptote here across here is at 1, because in the purple here I have an asymptote at 0, and I shifted everything up 1 unit. So this graph is negative 4x plus 1. So I took the original graph and then showed how these transformations apply. Let's do the same thing with part C. So in part C I have 2 to the x plus 3 power. How does that affect the graph? Let's see. The plus 3, what does that do? So first of all, let's graph 2 to the x, which we know is going to cross at 1 here and kind of go up like that. Now, think for a moment. If I say 2 to the x plus 3, if I plug in 0 for x, now I have 2 cubed. Instead of at 1, I'm at 8. Actually, I would need to plug in negative 3 in order to have 2 to the 0. So what this thing does, and we've seen the same transformation with polynomial functions, is it shifts everything over 3 units. So where my graph did cross at 1, it's going to hit 1 now at negative 3, and it's going to do something more like this. Okay, and this would be the point 0, 8. And you can verify that. h of 0 is 2 cubed, which is 8. And here at negative 3, I hit the value of 1. So it shifted the graph to the left 3 units. I hope this makes sense. We're going to look at exponential equations. We're going to look at applications of exponentials, and those things are very useful. Understanding the graph, though, is important. If you have any questions on this, I'd be glad to help, and thanks for watching.